Hello, pre-calc students. It is the start of a new unit. Unit 6 is going to be on exponential functions, and we're going to start today by sketching exponential functions. We don't need a calculator to do our sketches of exponentials. We might make tables at first to kind of get a general sense as to what the graphs look like, but then after that, we're going to base our knowledge of transformations on what we do with our sketching. So we'll get into that in just a little bit, but if you want to take out some paper, we're going to take some notes by hand, and we'll go from there. So to get started, let's compare what the two graphs look like below for y equals 2 to the x and y equals 1/2 to the x. Exponential functions are, of course, when the x is up in the exponent. Seeing what that graph looks like is compared to when x is in the base of the function, right? So when x is up in the exponent, that's when we know we have an exponential function. And like I mentioned, it might be nice to make a table of values such that we can analyze what this graph looks like. So we want to see how it behaves on the left side of the x-axis and the right side of the x-axis. So choosing -2 to 2 for a domain to get started seems like a good idea. And if I start with something like 2 to the 0, 2 to the 0 is 1. 2 to the first is 2, and 2 squared is 4. So this was a little bit easier probably to identify. 2 to the negative first, remember 2 to the -1 is the same as 1 over 2 to the first, which is 1/2. Similarly, 2 to the -2 is 1 over 2 squared, which is 1/4. And therefore, 2 to the -3 would be 1/8. And you're going to see that those values will get smaller and smaller and smaller and smaller. However, will they ever reach 0? And I'm hoping what you're thinking is no, they will not. So 0, 1's the y-intercept. We had 1, 2, and 2, 4, and plot as many points as you need to see that the graph and general shape of the function looks something like this for 2 to the x. Okay, moving across the way to 1/2 to the x, maybe you already remember or you have a good idea at this point as to what this graph's going to look like. But if you make a table of values similar to what we just did for 2 to the x, where we choose our x values from -2 to +2, the easier side is probably the positives again. 1/2 to the 0 is 1, 1/2 to the first is 1/2. 1/2 squared is 1/4. When you raise a fraction to a negative power, you can make it positive by flipping the fraction over. So this actually becomes the same thing as 1/2 to the -1st. It's the same as 2 to the first, which is 2. And this is the same thing as 2 squared, which is 4. So you can check me out on the calculator there if you are unsure about some of those. But once I have those values decided, now it's just going to kind of reverse, isn't it? So on the left side, when x is -1 or -2, it's going to grow faster on the negative side of the x-axis. At -1, you get this y value of 2. At -2, you get a y value of 4. And then you have 0, 1 again. And now you're going to decrease. But plugging in large values of x will not ever allow us to reach y equals 0. Thus, based on our last unit that we just finished up, we know we've got some asymptotes going on here. So now that we've seen the graphs of these kind of basic functions here, let's get some general sense as to what's going on with properties of graphs of the form y equals b to the x. So anything in general that has a base to the x power, let's talk about some of the general properties that we would notice based on that. So let's talk first about the value of b. So what we see is if b is bigger than 1, like this example over here. If b is bigger than 1, then we have something that's increasing over the domain, right? And we call that exponential growth. Meanwhile, when b is between 0 and 1, and those are the qualifications we have to give there. When we're between 0 and 1, then it's a decreasing function. And that would be called exponential decay. So those terms might sound familiar. You learn about exponentials as early as Algebra 1. You definitely do a lot more with it last year in Algebra 2. Okay, some other key features of functions of this form. Well, they all have the same y-intercept, because when you plug in 0 for x right here, you're going to get a y-intercept always at 0, 1, because anything to the 0 power is 1. So that's kind of a good point to make. Functions of this form, like we alluded to, all have a horizontal asymptote on the x-axis, so at y equals 0. So we're going to approach that line either in a decreasing fashion or if it's an increasing function on the left side, we'll see that happen. And then functions of this form do tend to have the same domain and range. So that's the last thing I'll comment on, domain and range. The domain is such that you can plug in whatever you want for x, right? Domain is all reals. But the range would be from 0 to infinity, right? We have no negative outputs for our y values here. So the range is only from 0 to infinity, excluding 0 as to where the horizontal asymptote is. So before we move on and do some transformations of those graphs up above, know that anything of the form like 3 to the x, 4 to the x, 5 to the x is going to look like this. And anything of the form like 1/2, 1/3, 1/4 to the x is going to have that exponentially decreasing nature to it. Okay. So I want to quickly, before we do a little bit more, compare the following on the same axes. So I'm going to graph A as y equals 4 to the x, B as y equals 7 to the x, C I'm going to make y equals 1/3 to the x, and D I'll make y equals 1/5 to the x. Okay. So if you want to give this a shot, doing it all on the same set of axes, it might start to look a little weird, so you might want to label your answers A, B, C, and D. Or I'm going to try and use some different colors here to make this all kind of make sense for us. But taking a look at, let's see, do I have some different colors? Let me grab this one. Okay. Taking a look at these graphs, how would, let's say, 4 to the x and 7 to the x compare? Well, those first two, hopefully you're looking at these and thinking that they are examples of exponential growth. And by the way, all 4 of these have the same y-intercept. They all have 0, 1 in common. But for the example 4 to the x, if 4 to the x has a general shape that looks like this, I'm going to call that graph A, how would 7 to the x compare? Well, 7 to the x on the positive side of the x-axis, it's going to grow a lot faster, right? I mean, 7 squared is 49, 4 squared is only 16. But on the negative side, it will come below 4 to the x, okay? It is going to decrease to 0 faster than 4 to the x would. So it will be lower on this side, but as soon as you cross the y-end, it's going to grow so much faster than 4 to the x. So that might be something like what B would look like. And you can probably use similar properties to talk about then what 1/3 to the x versus 1/5 to the x would look like. So on the positive side, again, 1/5 is going to be lower than 1/3. 1/3 will not kind of decrease as quickly as 1/5 to the x would. So if I start with 1/3 to the x, maybe I'll graph something that looks like this. For C, 1/3 to the x. So like I was mentioning, on the right side, 1/5 to the x is definitely going to be lower. But on the negative side, when you plug in negative exponents, and this winds up actually flipping over, it's going to grow faster than 1/3 to the x. Okay. Compare, for example, the input of -2. 1/3 to the -2 is 9. 1/5 to the -2 is 25. So this is going to grow a lot faster on the negative side. On the positive side, it's going to decrease to 0 faster. So just kind of a good sense of comparison, comparing some of the properties that we talked about up here of exponential functions of this form. So what we'll do now is let's take a look at some transformations of the form through, let's pick 3 to the x as our base. Okay. So we're going to look at some transformations of y equals 3 to the x. Now, if we call 3 to the x the parent function, we know what 3 to the x it looks like. It looks just like 2 to the x. Grows a little bit faster. But 3 to the x will look like this. Y-intercept at 0, 1. All the same properties essentially as 2 to the x up at the top. So let's compare the two graphs of y equals -3 to the x, and then we'll also sketch y equals 3 to the -x. And without a calculator, thinking about transformations, what those two things would look like. Now, if you wanted to make a table to figure this out, you could do that, but we should be able to do it without, because we know the effects that negatives have on a graph. When you negate x up on the exponent, negating x is going to flip it over the y-axis. So this is a reflection over y. Negating the base is like negating y, so this is going to flip it over the x-axis. So when I know that these two things represent reflections, take this graph and flip it over the x-axis, you're going to get a graph that looks like this. Still y equals 0 as the horizontal asymptote, by the way. But now we have an x-intercept at -1, or sorry, y-intercept at -1. Like I said, for 3, the negative x is going to flip it over the y-axis. So now you're going to get a graph that's decreasing as opposed to a graph that was increasing. The y-intercept stays in its spot. Horizontal asymptote is the same. And essentially what this is, 3 to the negative x, it's the same thing as the graph of 1/3 to the x. Using properties of exponents, this is the same thing as 1 over 3 to the x, which you can actually pull in as one base, 1/3 to the x power. Okay, so that's why it looks so similar maybe to this graph that was up here. 3 to the negative x reflects over the y-axis, actually winds up being the same thing as 1/3 to the x power. Okay, let's take a look at some other examples of transformations. For example, if I said, let's check out y equals 3 to the x plus 2. What does that effect of plus 2 on the outside have on the graph? Well, if I know what the graph of 3 to the x looks like, 3 to the x plus 2 takes the whole graph and shifts it up 2 units. So why am I drawing that special line y equals 2? The horizontal asymptote, which used to be here, shifts up 2 units with it. So the graph now looks like this. It has now a y-intercept at 0, 3, because it used to be at 0, 1. Take the whole graph, shift it up 2 units. So compare that to what if I had y equals 3 to the x plus 1 power? How would that affect what the graph looks like? Well, for 3 to the x plus 1, we're not adding or subtracting on the outside. That was the vertical shift. When you add or subtract up in the exponent, that's going to be a horizontal shift. And it turns out that it's the opposite of what we think should happen, like always happens with horizontal. This is going to move to the left 1. So we're not going to see a huge change here, but when we move it to the left 1, the y-intercept, which used to maybe be at 0, 1, is now at -1, 1. So if you think about taking that parent function, just picking it up and moving it to the left, it is going to change where the y-intercept is. In fact, the y-intercept, if you plug in 0 for x, would be at 3 to the first power, which is now at 0, 3. Okay. But transformationally, we should be able to sketch things pretty easily based on what we've done with transformations up until this point. So let's combine them into a couple different steps. What if I said y equals 3 to the x minus 2 minus 3? Uh-oh. Couple things at once here, right? So I draw a set of axes. What's going to happen compared to 3 to the x? Compared to 3 to the x, we're going to shift to the right 2 units, and then we're going to shift down 3. So 2 translations, right 2, down 3. If you kind of follow where the y-intercept moves, the y-intercept, if I go right 2 and then down 3, the new coordinate of the y-intercept is going to be at +2 and then -2, right? If I go down 3 from there. So it's certainly not the y-intercept, but I'm moving that y-intercept, I'm translating that point to its new location. The other thing I know is that since we move down 3, the horizontal asymptote moves down with it. So here's the new horizontal asymptote that I want you to sketch in, because when I go to make my graph here, for accuracy purposes, we want to make sure we're approaching the correct horizontal. And in this case, according to the vertical shift, it does move it down 3. So we get y equals -3 as that line there. What if I did something like that? Y equals 2 times 3 to the x. Well, 2 times 3 to the x, when we multiply by a scale factor like that, I hope what's jumping out in your mind is that we have a vertical dilation here. And that vertical dilation has a scale factor equal to 2. Because it's a vertical dilation, vertical means it's affecting the y values. So you're going to take all the y values and you're going to double them. So what happens to the graph, if I look at what 3 to the x looks like, I'm going to try and graph them on the same set of axes. if 3 to the x looks like this, then 2 times 3 to the x, if I think about taking all the y values along this curve and doubling them according to that scale factor, well, instead of having a y inted 0, 1, now you have a y inted 0, 2. And all these other y values would double here, and even though it's not growing very fast over here, doubling the y values will make them a little bit larger on this side as well. So you're going to see maybe not as big of an effect on the left side, but on the right side, when you get into the positive y value land, it is going to start to grow even faster than 3 to the x. A little tough to tell based on my scaling here, but there is some sort of vertical stretch that occurred. One quick note is that 2 times 3 to the x is not the same thing as 6 to the x. So for those of you that were at home just feeling silly, Mr. All, why don't you just multiply this to get 6 to the x? It's because it's not a thing. You're breaking PEMDAS, aren't you, if you tried that, right? So we don't want to break PEMDAS. You want to make sure that we're doing exponents before you do the multiplication there. So therefore, that is not 6 to the x. You have to take 3 to the x and think about dilating it by 2 to achieve the graph that we have there. So I think we've seen all the transformations, right? We've moved left, right. We've done some reflections. We've done some dilations. So maybe we need to just summarize everything at this point. If we say in summary, we now have extended our function of b to the x out as far as thinking something of the form a times b to the x minus h plus k. Wow, we start with just b to the x. Now we have all of this. And if we can do all of that to one function at once, we can transform it in many different ways. So let's talk about the value of a first. Okay, so a is going to be some sort of vertical dilation. It could be a stretch, or it could shrink the graph. If a was 1/2 or something like that, it might actually take the graph and compress it, right? Maybe make a note here that if a is negative, it's actually going to flip over the x-axis. Right, having a negative out in front attached to that vertical dilation, some sort of negative out there will flip it over the x-axis. Negating the x and the exponent would flip it over y. As far as the base of b goes, we know that b dictates whether it's exponential growth or decay. We've already talked about that, but b is bigger than 1 means that it's an increasing function, and b between 0 and 1 means it's decreasing. The value of h is going to be the horizontal shift to the left or to the right. So if h is negative, it's going to mean that we have to go right. And if h is positive, that actually means to go left, right? If it was x plus 2 up there, we would actually go to the left 2. Negative h means go right. And finally, for k, we follow the sign of k. So k is the vertical shift. You would go up. And for a negative k, you would go down. Okay. So the nice thing about this is that these are all the same types of transformations that we've seen for other functions throughout our sketches and our functions units. So I think we're actually at a pretty good stopping place. We might add on to this and do a transformation of all at once of all these different types of transformations when I see you in class next. But if you get the general ideas of the properties of how do we make these small changes to affect what the graph of a parent function like 3 to the x would look like, then we're in a pretty good place. All right. So if you have any questions, let me know next time I see you in class. Otherwise, have a good day.